Welcome to the lecture on in situ bioremediation and bioaugmentation. We'll talk about the requirements for bioremediation, what we're trying to do. We'll talk about the potential of different chemicals to be degraded. Talk about some redox problems and opportunities involved in biodegradation in situ. We'll look at some metabolites to get a sense of whether or not we can use those to indicate whether or not the reactions are being done successfully. We'll also have a look at some developing areas that allow us to look at the microbial community. That's a secondary line of evidence that, in fact, the community is responding to the stimulation we're providing. The key issue, and the area where contaminant hydrogeologists play the key role, is bringing together the additions, the contaminants, and the microbes to bring about in situ biodegradation. We'll talk also about some approaches for chlorinated solvents, and that'll lead us into an interesting discussion, I think, on bioaugmentation. So let's go with part one. So what is our requirement? Well, we have to create conditions favorable for faster biodegradation. If the biodegradation is already fast enough, we're practicing monitored natural attenuation. So we're trying to enhance the rate of biodegradation. This usually involves addition of electron acceptors, perhaps electron donors, often nutrients, and these are added either as a solution in water or in a gas phase. So again, transport of a liquid phase is involved. So again, we're trying to bring together contaminants, electron acceptors, nutrients, and microbes. Where are these in the subsurface? Well, as we've seen, contaminants can be mobile, dissolved in water. They can be sorbed on solid, ready to partition back into the water. Or in source areas, they can exist as non-aqueous phase liquids. Electron acceptor that we're going to add is probably mobile, although things like iron become fixed very quickly and may be immobilized. Nutrients, ammonia, for instance, as a source of nitrogen, is reasonably mobile. Phosphorus isn't terribly soluble, and so it's limited in its mobility. Microorganisms can move, but in general, people advise us to treat them as fixed or moving very slowly. So we're trying to bring the mobile chemicals to the microorganisms in most cases. So the requirements are, of course, to create the right conditions. What are those conditions? Well, we've provided us a table of conditions for the degradation of a number of common groundwater contaminants. For example, acetone here. You can see we've divided the environments into aerobic. That's something we would stimulate by oxygen addition. Nitrate reducing, stimulate by adding nitrate. Iron reducing, get some iron 3+ into the system. Sulfate reduction, add sulfate. Methanogenesis, add substrates that convert to methane. And we also had a category of general anaerobic where the dominant electron acceptor wasn't specified. What we're really looking for in these tables are conditions that are capitalized yes. Those are telling us that those are probably good target conditions to create to enhance in situ biodegradation. So for acetone, you would see we have a chance to add oxygen, add sulfate, or create strongly anaerobic conditions that support methanogenic bacteria. Adding electron acceptors may help us get rid of the contaminant of concern, but there are issues with many of those electron acceptors. For instance, adding nitrate to bring about denitrification might be a good idea for acetone. Nitrate's a contaminant. We'd have to make sure that the residual nitrate levels were acceptable. Iron. Well, iron's not terribly soluble. It's hard to add. It's also an aesthetic contaminant. Nobody likes a lot of iron precipitating in their pipes. Sulfate. Well, sulfate's a minor contaminant. Levels of 500 milligrams per liter usually aren't enjoyed. But one of the products of sulfate reduction is sulfide. And hydrogen sulfide's a very smelly and very dangerous gas. So if we're going to bring about sulfate reduction, we have to be concerned about the possibility of hydrogen sulfide. Fortunately, the sulfide is scavenged by metals in the subsurface, so it likely can be removed naturally, but that still requires us to pay attention. And again, methanogenic conditions. If we're trying to create methanogenesis, we're creating methane. And methane's explosive. So again, a number of these electron acceptors have issues that we have to be aware of. So, further on biodegradation potential. Again, we just give you this table. You can have a look at it. We don't claim it's correct or the best. You can always talk to microbiologists or remedial specialists who have experience, and they can perhaps suggest improvements on this table. Again, more table. More table. And more table. Okay, let's move on to redox issues and opportunities. Typical way for us to represent the subsurface environment is in terms of EH or redox level and pH, acidity, alkalinity. So on this diagram, EH increases upwards. So at the top it's more oxidized. At the bottom the groundwater is more reduced. And you can see we're looking at iron speciation in water under various EH-pH conditions. And I've highlighted in green areas where iron 2+ is soluble, and areas in pink where iron 3+ is not soluble. Iron 2+ dominates in the reduced environment, iron 3+ dominates in the oxidized or aerobic environment. Well, what if we were to add oxygen to get BTEX to biodegrade? The BTEX likely exists in an anaerobic plume, so it exists somewhere down in this area. And in fact, most BTEX plumes have a considerable amount of dissolved iron because it is in the area where iron 2+ is quite soluble. So by adding oxygen, we increase the EH level. We move up. That takes us into the area where iron 3+ is a dominant iron species, and it's not soluble. So we get precipitation. Unfortunately, often on the well screen where we're adding oxygen. That becomes an issue. We might want to add iron 3+ to promote iron-reducing bacteria. Well, we can see that under these conditions, it's not soluble, and iron 2+ dominates here. So is there some place where iron 3+ is soluble? Well, yes, under extremely oxidized, extremely acidic conditions. Very unlikely that bacteria will enjoy those conditions. So again, we get limits on what we can do and some suggestions of what we have to be aware of when we start bringing about changes in the subsurface. So let's have a quick look at indicators of active biodegradation, this idea of metabolites. Metabolites are the product of the reaction that we're trying to induce. So for BTEX, we can go into the literature and find examples of metabolites. These are breakdown products, intermediate breakdown products, that will subsequently carry on breaking down until they reach CO2 and water and very simple chemicals like that. One of the metabolites of aerobic benzene biodegradation is benzene 1,2-cis-dihydrodiol. It's apparently quite unique. So if we find this chemical, we can confirm that benzene, in fact, is undergoing aerobic degradation. Similarly, benzyl succinate is distinctive for the degradation of toluene, but under anaerobic conditions. Unfortunately, many other metabolites are not unique. So it'll tell us that some degradation is occurring. It may not tell us which chemical is degrading. It may not be specific as to the environment in which the degradation is occurring. Chlorinated compounds degrade, and we've seen this already, that we often see a sequential degradation. So trichloroethylene could degrade in one microbial step all the way to ethylene, complete dechlorination. More commonly, it appears to undergo a series of degradation steps, each catalyzed by an enzyme. And so to get TCE all the way to ethene, we might need a number of different catalysts. And that may mean then we have a number of sequentially produced metabolites. These are quite easy to analyze, and so we routinely have access to this information at contaminated sites. Again, we noted that cis-1,2-DCE is the dominant microbial product of dechlorination of TCE. But we note that we can get to the same product by a three-step process or a single-step process. So again, at least ethylene is not an absolutely clear evidence of the microbial pathway being taken. Good evidence of a reaction, however. So in many cases, metabolites can provide strong, or in some cases, benzene case we just did, compelling evidence that some biotransformation is occurring. It also tells us something about the nature of that biotransformation. So I think it's very good information to have. It's sort of a secondary, after you note that benzene mass seems to be lost, then being able to say, well, the metabolite of benzene biodegradation is present, tells you at least some part of that process. Unfortunately, many metabolites are not specific to compounds. They'll give you a general view of things degrading, but not necessarily specific compounds. And again, metabolite might be characteristic of the environment of degradation as opposed to what chemical is specifically degrading. We've also noted in previous lectures that stable carbon and hydrogen isotope analysis may have that same function. So we've introduced now bioremediation, a little bit of caution about EH, pH changes, a suggestion that metabolites might be useful to look for, and we've reviewed the degradability of compounds. We'll proceed a little bit further on the microbial aspect on the next lecture, and then proceed to the applications, which are more of interest to us, I think. So until next lecture, thank you.